Hi everyone, welcome back to my channel. Today I'll be going through Singapore Chinese Girls School P5 Science. This is their 2024 Term 2 weighted assessment paper. So this paper is totally on water cycle. Okay, water cycle. And usually water cycle you involve a component which require you to know matter, and another part will be heat. Matter and heat. So these are the few things that you need to take note. And if you want to break them down, right? Matter, you need to know solid, liquid, gas, and this part will be your gain heat, and lose heat. Okay, so you need to combine more or less these ideas together to be able to get a sense of how to answer water cycle questions. Okay, so I'll go through the MCQ first, then followed by the open-ended question. So question 1, the diagram below represent the change of state of water: solid, liquid, gas, and you have A, B, C, D. Which one occurs in the water cycle? Okay, water cycle, which process will occur in them? Okay, so in this part, the water cycle, right, there will be two processes: evaporation and condensation. Okay, these are the two processes. So from there, we really need to identify where is evaporation, where is condensation. Evaporation will always be from liquid to gas. Condensation, gas to liquid. So in this case, evaporation will be this. Evaporation. Okay, then this will be condensation. Okay, so the answers will be D and D, number 2. Okay, some may say that how come it cannot be A and C? Okay, A and C, this part is melting, freezing. Then some may question, actually in some part of the country, they may water cycle may consist of the melting and the freezing process. That is only when you see snow. Okay, snow or hail, then you will need to involve freezing and melting. But in this case, it is when we are talking about the water cycle, right, usually we refers to the water cycles that more or less applied to our own country, in this case Singapore. Okay, for Singapore, the water cycle only involve rain, cloud, and water vapor, okay, which is invisible, is a gas. You don't really see them. We don't really involve snow and hail, so this part we don't really consider them as part of the water cycle in Singapore. But maybe in other countries, they could have involved this process as well. Okay, so the answers for this is really much applicable to Singapore water cycle. So answer is number 2, B and D only. Okay. So over here, which of the following are ways of conserving water? Okay, conserving means save water. Okay, so this one very clear cut. Let's take a look. Washing dishes under running tap water. No, this one you are wasting water. Wasting. Okay, for this part you're wasting, because you could have take a basin of water, put the dish in it, and then wash it, and this could prevent the water to be running throughout the whole time. Use water that was used for rinsing clothes to wash the toilet. Yes, this one, yes, you are reusing water. Okay, use water that are used for washing vegetable to water plants. Yes, you are reusing also for other purposes. Okay, reusing. Okay, use a piece of cloth and pail of water to wash car. Yes, this one will be a way to save water. So B, C, D, number 4. Okay, what is not a way to conserve water for D is you take a water hose, go and spray the car continuously. Then you are indeed kind of wasting water. Okay, so B, C, D is the correct answer for question 2. Okay, now we move on to question 3. 3 beakers of water at different temperature. Different temperature will place at a room at 28 degrees. So it's trying to tell you that the surrounding air is 28 degrees Celsius. Surrounding air. Okay. The diagram shows the observation after 10 minutes. So after 10 minutes, you can see the water droplets on the inside. This one is on the outside. And this one got no water droplets. No water droplets. Okay, these are the observations. Which one shows the correct temperature of water in beaker A, B, and C? Okay, so first up, when you see no water droplets, the water temperature must be the same as surrounding. Okay, for C, no water droplets. Okay, so the water in beaker C is same as surrounding. So straight up, C is 28. So this is either 1 and 3. Okay, so the reason why C must be at 28 degrees Celsius, right, when you see no water droplets, right, is because the water vapor, be it in the surrounding or inside the inside the beaker, right, would not be able to lose heat and condense into tiny water droplets because they are at the same temperature. Because for condensation to happen, you need the warm water vapor to lose heat, then it can condense. So for it to lose heat, the warm water vapor must be of a higher temperature. Then it can start to lose heat. Okay, so in a nutshell, you want to see water droplets, you need to have a temperature difference between water vapor and condensing surface. Okay, and the water vapor, right, must be at a high temperature or higher temperature. This condensing surface, or it could be a parcel of cooler air, must be of a lower temperature. Then condensation can happen because the warm water vapor can then lose heat to the condensing surface and condense from there and change into your tiny water droplets. So B and A confirm have condensation because you already see water droplets appearing. Okay, so the trick is once you see the water droplets on the outside, it must be way colder. The water inside must be way colder than the surrounding. So this one must be cold water. Okay, this one must be cold water. This one must be hot water. Okay, maybe I'll put hot, cold. Okay, maybe I use colors. Cold water, hot water. It must be this. Okay, so what happened during what happened for the cold water, right? Is that right? The warm water vapor in the surrounding air will come into this surface. Okay, because this surface, right, we will assume that it will be the same temperature as the cold water, right? So it will be a cooler surface area. This will be a cooler surface area. So the warm water vapor will then be able to lose heat to this cooler surface area and then condense into a tiny water droplets which form over here. That's why when you see water droplets on the outside, the water inside must be always of a lower temperature than the surrounding. Okay, so in this case, it must be less than 28 degrees Celsius. So if you take a look, B must be less than 28, then answer must be number 1. Okay, then A must be 80 degrees. Okay, so what happened over here is that the warm water vapor is evaporating from this hot water. Evaporating, then it came into this contact. This surface, it will start to lose heat to this surface over here, and then it will condense to form your water droplets. Okay, because usually this part we will more or less assume that it is very close to your room temperature. Then the water vapor that is starting to evaporate from it, right, will be of a higher temperature. So we can take it as, if let's say it's 80 degree, right? So this warm water vapor of 80 degree will lose heat to this surface of 28 degrees. Then it will start to condense into our tiny water droplets which appear on the inside of the lid. Okay, so from here, this answer is number 1. Okay, everyone, welcome back to question number 4. Substance X is a solid at 25 degree, liquid at 190. So which of the following is a possible melting and boiling point of X? So one way to very quickly to know this, to know the melting point of X, if you already know that the substance is a solid at 25 degree, that means the melting point is greater than 25 degree. That's one thing for sure. Okay, so if you look at it, if melting point must be greater than 25 degrees, only 3 and 4. Then the liquid, right, for the boiling point, right, if we know that the liquid is the substance X is a liquid at 190, right, that means the boiling point must be greater than 190. This is a very, very quick way to know it. So the only option between 3 and 4 is 3. So the answer is 3. Okay, for this question. But there's another way to do it. Okay, if you want to know it for sure very, very quickly. So if I were to do it along with the correct answer, let's say I draw a temperature line. Right. This will be the marking of the melting point and the boiling point. So that means any numbers that fall here will be solid. Any number that fall here will be a liquid. Any number that fall here will be a gas. This is another way to do it. Then you just match accordingly. 25 degrees, it will be somewhere here. 25. Okay, 25 degrees will be somewhere here. So it matched because at 25, X must be a solid. Then you move on 190. 190, it cannot be the green color. It must be at the blue color somewhere around here. So 190. So at 190, it is a liquid. It matches with C. But if you do 1, 2, and 4, it will not match. So that's why the answer is C. You can use this technique, which is what we call a temperature line. You always arrange the smallest number over here, then here will be a larger number. Then from here you can kind of know it. Or if you already have some information held to you, you can use this information to deduce the melting and boiling point. Okay, so let's move on to question number 5. So Clarice heated some liquid in a beaker until it is boiled. Okay, so at first it's a liquid, then it kind of reached to a boiling point. Okay, since it did not tell me it's a water, I couldn't assume that it is always at 100 degrees because only water will boil at 100 degrees. Okay, she continued to allow the liquid to boil for some time before it was left on the table to cool down. She plotted the graph using the result obtained from the experiment. Okay, so in this case, you have P, Q, R, and S. Then one way to really deduce the graph, you take a look at this part. This part must be boiling. Okay, because it heated some liquid. So before that, the liquid will have gained heat. The temperature will start to rise. Okay, until some point, if it boils, right, then the temperature will remain constant. Temperature constant. So that means this part is the one that she heated. Okay, then Q and R is the part that where the temperature remain constant, where we know that the liquid reached boiling stage. Okay, then after that, she left it on the table to cool down. So this part over here is left it on the table to cool down. This portion. Okay, so R to S left it on the table to cool down. That's why the temperature start to decrease. Okay, there's a heat loss to probably to the surrounding. Okay, so over here, which of the statement is correct? There's no heat gain Q and R. Q and R, as you know, this part is boiling. Boiling always have heat gain because we always write this. Okay, we always write gain, heat, and boil. Okay, so there is a heat gain portion. Okay, so this is wrong. Okay, and even though the temperature remain constant, it doesn't mean there's no heat gain because the heat gain or the heat gain by the liquid, right, is used to change in state. It was not used to rise in temperature. Okay, so that's why the temperature in this case more or less remain constant because it was used to change the state of the matter. Though there is a heat gain, there is heat gain. So this is wrong. Okay, the liquid lose heat at R and S? Yes, because the temperature went down. Temperature went down, we can always infer it as loose heat. Okay, number 2 is correct. So number 2 is correct answer. Okay, the melting point of the liquid is 30. Okay, it seems to tell you that because this graph read at 30 degrees, it doesn't mean it is the melting point. Okay, in order to know whether it is a melting point, you need to at least involve two things. You need to have a solid, and you must change in state at the liquid. And this change in state, at some point, the temperature will remain constant. Temperature will remain constant when there is a change in state between solid and liquid, which we call it melting. Then there is a part where we will know that there is melting, and if it indeed happen at 30 degrees, then we can tell. But in this case, we can't tell. Actually, this statement does not make sense to the graph. So number 3 is wrong. The change of state of liquid occurs only at P and Q and R and S. There is also a change in state of liquid at Q and R, which is boiling. Okay. Boiling involves the change of state from liquid to gas. So that's why this statement is wrong. Okay. It should be PQ, RQ, PQ, QR, and RS. So sorry, it should be here. Okay, it should be here. Change of state, change of state, change of state of liquid. Okay, why is it change of state of liquid? This part is evaporation, evaporation plus boiling, because evaporation will happen at any temperature, right? This part there is also evaporation. Even though the water is cooling down, but some of the water will be evaporated into water. Some of the liquid will evaporate into into a gas as well. Okay, not water vapor, because this question really did not tell us that it is water. Okay, so in this case, this should be how you would interpret the question. Okay, so that's why number 2 is the correct answer. Okay, because only number 2 will fit into the graph. Okay, so let's move on to question 6. James placed 3 identical towels containing the same amount of water in a balcony to dry. Each towel was folded such as their exposed surface area was different. So they are trying to tell you that exposed surface area is different. The word different tells you that this is a change variable. After 2 hours, each towel was weighed. James recorded his result and plotted the graph. Okay, which of the following is the most suitable label, okay, for P and Q? Okay, so there's a trick you can kind of use. If you see there's one line in the graph, usually the change variable is here, the measured variable is here. So this will be your cause, this will be your kind of your effect. Okay, since we already recognize that the change variable is the exposed surface area, because the word different is being used, it suggests something is being changed, or there's a variable that has been changed, and this variable is your exposed surface area. So this will be ESA, exposed surface area for Q. So it could be number 1 or 4. Okay. Okay. So it's either time taken or mass of towel that was used as a measured variable. So you take a look. After 2 hours, each towel was weighed. These give you the clue of a measured variable. If you are weighing the towel, you are weighing how much water has kind of evaporated. Okay? So in this case, it will be your mass of the towel. Okay? Because you are using the mass of the towel as an indicator to tell you how much water has been evaporated. Okay? So, but there's nothing mentioned about time. In this case, so time will not be the measured variable that we are looking into, or it is not the result that we are measuring. Okay, okay, so this one is number 4. But on a side step, can time be the measured variable? In this case, yes. If let's say the question say, I want to find out how the amount of time for the 400 gram of towel, right, reach to 200 gram. Okay, I want to find out the time for each to reach. Okay, and of course, the faster the time to reach to 200 gram, right, it means that the water evaporates faster. It can be, but in this case, it is not applicable because the question already tell you each towel was weighed. So this will correspond to the measured variable. Okay, so this will correspond to the this was correspond to the change variable. So the kind of the information are more or less in the question. You just have to pick them out accordingly. Okay, so okay, let's move on to question number 7. A small block of ice was placed in a paper cup covered with lid left in the room. Okay, so you can see water and you can see block of ice. So you can see that this block of ice, there's still some water at the side. So it must tell you that this process is melting because it exists between two states, solid plus liquid. Is in the process of melting, haven't melted yet. Okay, then they ask you what will happen to the temperature of the air in the paper cup and the melting ice after 2 minutes. So let's take a look. The air will be somewhere around here. Okay, so what will happen to the ice block first? You think about it. What will happen to the ice block first? The ice block, the temperature is the ice block is melting, so the temperature will remain constant because melting takes place at 0 degrees. It's a constant temperature. The temperature will only start to rise when you see the whole cup is fully filled with water. That means melting has completed. Okay, completed when the cup is fully filled with water. That means there's no more ice left. Okay, there's no more chunks of ice left. That is usually when the temperature of the water will start to increase, because we already take it that melting already completed. Is fully in liquid state. Temperature is the water will start to gain heat from the surrounding and increase in temperature. Okay, that means the amount of heat gained from the surrounding is no longer used to change in state. It's used to raise the temperature of water. Okay, so in this case, temperature of melting ice will remain the same. Okay, so number either 2 or 3. The temperature of air in the cup. So you take a look at this portion. Will it increase or decrease? So the ice in this case, they will want to do one thing. They will want to gain heat from here, right? Gain heat, okay, from the air in the cup. So that means the air in the cup would have lose heat. Okay, maybe it will be better if I use blue color. Okay, it will lose heat to the ice, and therefore when it lose heat, the temperature will become lower. So it must have decreased. Okay, so this is one way to look at it, because the melting ice must have gained heat from the air in the cup, right? So the air must have lose heat to the ice. So in this case, the temperature decreases. Okay, so temperature decreases. So the answer is number 3. Okay, this is how you can kind of interpret whether it will gain heat or lose heat. Okay, so let's move on to the last MCQ question. Okay, this one is a little bit more tough than usual. Okay, John used a setup shown below to obtain pure water from seawater. After an hour, 50 ml of pure water was collected in the beaker. So you have the beaker, you have the whole container, you have the glass dish. Okay, then which of the following methods will allow more water to be collected in an hour? So you want more pure water to be collected. Okay, so let's take a look. If you heat the seawater up, will you have more water collected? Yes, because when you heat the seawater up, the temperature increases, the rate of evaporation increases, so there is more water vapor in the setup. So more water vapor will leads to more condensation. So more condensation, you have more water droplets dripping into the pure water. So this is how the setup will do. So the water vapor will evaporate off from the seawater at a faster rate. So it will condense here, or they will condense more. Okay, so when it condense more, you have a V shape, right? So it will drip into the it will drip into the beaker collected as pure water. Okay, so temperature increase, rate of evaporation increase, more water vapor, more condensation, more water droplets. A is correct. Warm up the glass dish. No. Okay, this couldn't be the case, because when you warm up the glass dish, right, what will happen is that the warm water vapor over here will lose heat slower to this glass dish because this is less cooler now. Okay, so one thing that you have to take note that is that the rate of condensation depend on one factor, the temperature differences between the water vapor and in this case will be the glass dish. Okay, the greater the temperature difference, the greater the rate of condensation. So let me put to you in this portion. So suppose you have water vapor, you have glass dish, and this is the temperature difference. Temperature difference, right? So let's say that the first scenario, which is not part B. So the original scenario, let's say the water vapor is at 50 degrees, the glass dish is at 10 degrees. So the temperature difference, you minus off away. The temperature difference is 40, right? So we are using this to tell us the rate of condensation as a way of comparison between B. Okay, so what we mean by when we want to warm up the glass dish, that means the same 50 degrees water vapor in the setup meet with this glass dish that is of a higher temperature. Then you raise it up. The temperature is warmer, right? Warm. Okay, so now because you have a way warmer temperature, the temperature difference when you minus off, the temperature difference is 30. So the temperature now, the temperature difference is now smaller as compared to this. So the rate of condensation is lower. So you have less water droplets condensing. You have less pure water collected. So this one is wrong. Okay. So on this portion, so that's why answer B cannot be correct. Okay. So we take a look at C. Use a narrow beaker. So you take a look at this beaker. You make it narrow over here. That means the amount of exposed surface area the seawater have, will become larger. If I were to make this, okay, if I were to redraw this, okay, this is a narrow beaker. So the amount of exposed surface area originally is something like this, right? But now if I make the beaker narrower, this is the amount of exposed surface area. So from this become this. So the exposed surface area become larger. Okay. So you have larger exposed surface area. Same thing, rate of condensation increase. More water vapor, more condensation, more water droplets. C is correct. So answer is A and C. Answer is number 1. Okay, because the rest, because you cannot find another option with A, C, D. Okay, so answer must be A and C. Okay, but D is wrong. Okay, D is wrong. Okay, because even when you pour the more seawater in the container, right? Let's say I pour here. Okay, it will still have the same exposed surface area. The temperature is still the same. In this case, we will assume that it's the same, right? It's just that the water become more. Okay, exposed surface area is the same, so the rate of condensation is the same. The amount of water collected, the amount of water vapor evaporating from it will be the same, and the condensation will be the same. The water droplets will be the same after an hour. Okay, so this part is very crucial. After an hour. Okay, if we are talking about if time is not a factor, then you will have more water collected. But since time is fixed, right, whether you pour more seawater or less seawater, right, it's still going to have the same amount of pure water collected. If indeed we do carry out the experiment for 1 hour. Okay, but if time is not a factor, then if you have more seawater, more pure water will be collected because there is more water that can evaporate off from the seawater. Okay, so answer is number B, A and C, B and D is wrong. Okay, so this part is more or less for the MCQ. Okay, so now we move on to the open-ended question. Okay, 9 to 12. Okay, so question number 9. The diagram below shows the water cycle. We have rain, sea, rivers, lake. This is water bodies. Okay, they are given different names. Okay, then evaporation. Okay, so this one you have to take it that this is a liquid. This is liquid. Evaporation, when evaporation occur, right, liquid will become gas. So straight away P will be your water vapor. Yes, water vapor is a substance within the water cycle, but it's just as invisible. Okay, Q will become back your liquid, but it appear as your cloud, okay, which is on top of your sky. And then you have B again. B is just rainfall. Okay, B in this case will be your rainfall, but there's nothing to talk about B, so we can don't talk about it. So water vapor and cloud, this one very straightforward. Similarities between evaporation and boiling okay, similarities is always this. Okay, change of state from liquid to gas, boiling. Okay, but both of them involve gain heat. So the key idea is liquid become gas, both of them when they are heated. Okay, so you can write something like both involve a change of state when liquid gain heat become gas. Okay, differences, you can have two differences. Okay, so I offer you two types of answer. So evaporation occur at any temperature, but boiling is fixed. Boiling is fixed, evaporation any. Okay, or another things that you can take note is that let's say you have a beaker of water. Okay, this is okay, maybe I should have used beaker. This is water. Okay, evaporation will be here. Okay, evaporation will occur here. Evaporation. Boiling will occur here. Boiling. Boiling is throughout the liquid, all the way from the bottom of the water column, bottom of the water, all the way to the top of the surface. But evaporation will always be at the surface. That's why we always say that the exposed surface area will affect the rate of evaporation, because the larger the surface, the greater the rate of evaporation. Okay, so evaporation occurs at the surface, boiling occurs throughout the liquid. So this is another differences that you can take note. Okay, so on this portion, okay, Rachel carried out an experiment as shown below. She placed identical ice cube and the same amount of water in each beaker. Okay, this is trying to tell you a fair test component, a fixed variable component. Okay, fixed variable. Okay, identical test tube. This is also fixed variable. So okay, then the only things that has been changed is the ice cube that is broken into different amount of pieces. So when you talk about the when you're testing about different the ice being broken up into different pieces, right? The change variable is really the amount of surface area in contact with water. Okay, so it should be the amount of exposed surface, amount of surface area of the ice cube in contact with the water. Okay, so in this case, this will be a change variable. So some of you may think, why we don't use the word exposed in this case? Usually exposed, we are talking about the, let's say, exposed is the ice cube left on the table exposed to the surrounding air. Then we will use the word exposed. But in this case, it's not exposed to the surrounding air because it is in contact with the water. Okay, it's touching the water. Okay, water is something that you can see. That's why we don't use the word exposed, but rather we use the word surface area in contact with water. Okay, exposed, usually we talk about solid to gas or liquid to gas interaction. Okay, this one is solid to liquid interaction, so we can use the word surface area in contact. Okay, on this portion. So this is just some mini differences when to use exposed, when not to use exposed. Okay, so she recorded the time taken for the ice cube to melt completely. Okay, then they give you the beaker 1, 2 and 3, then they give you the average 3 readings. Okay, and you notice that this one is not, beaker 1 is not broken into any pieces, right? So this one will have the least surface area. This one have the most surface area. So this is something that you can keep in mind. Okay, and you notice that the most surface area, the time for the ice cube to melt is the least. Okay, while if the most surface area, the time taken for the ice cube to melt completely is the least, while the least surface area is the most. This is something that you can take note. Okay, so what melting means? This is a definition. It's asking you to make a definition. A definition statement. So you can talk about three things. Okay, you can talk about change of states. Okay, this is from solid to liquid. Then you can talk about the heat transfer. Number 2, heat transfer. So this will be your gain heat. Melting require you to gain heat. Then you can talk about occurring at fixed or any temperature. Okay, and obviously melting is fixed temperature. So the main idea is solid to liquid, gain heat, fixed. So in this way, you can straight away write it in this way: solid gain heat and become liquid or change in liquid at a fixed temperature. So the three components are this: solid, liquid, gain heat, fixed temperature. You just have to put these ideas into a statement. Okay, using this method, you can apply to any water process definition like freezing, evaporation, condensation, all these processes. Okay. Why did Rachel take more than one reading? Okay, why did she take more than one reading? This is a why. Okay, so you have to look at it in this case. This is a case about repeatability. Okay, when the readings are being repeated, one thing that they want to bring out to you is reliability. Okay, when you repeat the experiment, it's always about reliable. Okay, you want to check whether the readings that you take, are they reliable? Can you trust it or not? Okay, so imagine if you take only this set of reading, you only take one. Okay, and then let's say you accidentally make mistakes. Okay, let's say this is 30, right? Okay, then it seems that if you use this set of reading, right, then the conclusion that you made that it could be that the surface area, it seems that it does not really affect the time taken for the ice cube to melt completely. But if you take more readings, then you check again. How come this one 80 and 30? Then you know that something is wrong. It could be the first reading is wrong or the second reading is wrong. You don't know. That's why the third reading come into place. Okay, third reading. Okay, from there, the third reading, you most likely, if you got 84, 85, and 30, you should already know that the one with the 30 is wrong. Because these two, when you repeat more times, right, you have more confidence in these two readings that these are the correct ones. Because the result appear more times. Okay, so when you are repeating the reading, it gives you a sense of confidence that your reading is more or less correct, and it allows you to check against whether your readings is indeed trustable. Okay, that means when you do it at the same time, do you get the same result? Okay, that's the idea of repeating your reading, or in other words, reliability in a science experiment. So in this way is to really when you take more than one reading, you want to do one thing. You want to check that your results are consistent and they are reliable. Okay, these two parts are the key important words to ensure that the result are consistent and reliable. Or you can even say that to check for consistency and reliability. Okay, you can put it into a noun instead. Okay, so in this way, in other words, right, sometimes they will ask you how do you ensure that the result is reliable? How is a suggestion. Okay, how do you ensure that the result is reliable? Okay, then there's two parts. You repeat 3 times, then you find average. Okay, these are the two ways that you can increase the reliability. How you do it? This is why you do it. Okay, when you do it for 3 times, you are checking for this. Okay, but how to how to make sure that the result is reliable, you do this. So that there is a differences between the two of them when it comes to a how and a why question, when it's related to repeatability of your experiment. So you need to know when to use this and when to use this part. Okay, so explain why the ice in beaker 3 took the shortest time. Okay, took the shortest time to melt completely. So this must be related to the surface area. So this part you can explain it in this way. Okay, beaker 3 had the most surface area in contact with the water. So the ice will gain heat fastest from the 50 degrees water and melt fastest. Okay, so this will allow you to be able to answer the questions completely on this part. Okay, so let's move on to the next portion. Question number 11. Alex prepared to set up A and B with same amount of water but at different temperature. Okay, different and same. They always try to tell you something. Okay, this is 27 degrees. And you notice that the water is also at 27 degrees, right? So same temperature. Same temperature, straight away, no condensation. So you will not expect water droplets to form, whether on the inner layer or outer layer. Okay. After 5 minutes, right, the reading of two setups are shown below. Okay, so A 250 at the end is 250, so no change. This is no change. Okay, B is 250, then 254, add 4. Okay, add 4 more grams. Okay, so there's an increase. Then they ask you why the reading of the digital balance increases. So you have to take a look at this part. So this one, you notice the temperature is lower, right? Temperature lower. So what will happen to the warm water vapor in the surrounding? Warm water vapor at the surrounding will be more or less at 27 degrees Celsius. So when this warm water vapor in the surrounding, right, at 27 degrees Celsius, it will meet with this surface, right? This surface over here will be 4 degrees Celsius because the water is at 4 degrees Celsius, so the cup will have loose heat to the cold water until it reaches more or less 4 degrees Celsius. So the warm water vapor meet with this 4 degrees Celsius the surface, right? It will start to lose heat, then it will condense, and it will form your tiny water droplets. Tiny water droplets. Okay, and this will appear here. Okay, but these tiny water droplets, right? It is still water. It is still matter. It has mass, and the mass will contribute to the reading over here. That's why it will become 254 after a while. So this is an exact explanation. Okay, but when it comes to writing this part, there's a few things that you need to take note. So that's why I show you this portion. You need to probably write warmer water vapor or warm water vapor. Okay, from where? You need to tell me where is the source. Source of water vapor. Okay, be it could be from the evaporation process or it could be from the surrounding air. Loses heat to the cooler outer surface of the beaker, condense into tiny water droplets. So there's actually 5 main components. Warm water vapor, from where? Lose heat, cooler, condense, tiny water droplets, which added more mass to the setup. So if I want to put it into acronym, I will put it this way: WLCCT. Okay, so usually I will tell my students in this way. Okay, after you write this, you check whether you got W. Okay, you have W, right? Okay, cancel. You have W here. L loses heat, cancel. Cooler, cancel. Condense, cancel. Tiny, cancel. So this is a way to make sure that you have all these 5 so-called elements. Okay, that's inside your answer to describe and explain a condensation question. Okay, this is how you will need to be able to do it. Okay, and there's a funny acronym you can remember it. You can say we love to train, and you notice that this is warm water vapor loses heat to the cooler surface area, condense into tiny water droplets. So this is one way to remember it very, very, very quickly. Okay, so in the exam, you can write it at the side. Then once you write finish, you check and cancel off. Okay, see whether you have all these 5 elements. Okay, another way to answer this is this, where we swap the placing for these 2 parts. Okay, so it'll be warm water vapor from the surrounding air came into contact with the cooler outer surface. So WC first, then LCT. So this will be the WCLCT. Okay, which unfortunately I did not have any acronym to talk about this, but this is one way that you can think about it. A warm water vapor from the surrounding air came into contact with the cooler outer surface of beaker B, loose heat condensed, form your tiny water droplets. Water droplets on the surface added more mass to the setup. Okay, this is a little bit long-winded way. Okay, so explain the purpose of the layer of oil. Okay, the layer of oil is to prevent the evaporation from occurring. Okay, because if you don't have this layer of oil, water will start to evaporate into water vapor. So if it's evaporate into water vapor, it's no longer in a setup. No longer in a setup, then the mass will start to decrease. Okay, the mass will start to decrease. Okay, in this case, we want to check and make sure that the mass of the setup increase is indeed due to the condensation. Okay, we don't want the evaporation to play a part in this factor. That's why in this case they probably put a layer of oil. We don't want evaporation to affect the experiment. Okay, so in this case, it will be to ensure that the evaporation of water does not occur, and it will not affect the experiment. Okay, so question number 12. Okay, Andy poured some water on a flat plastic board and covered the board with a transparent cover. He left the board in the garden and measured the size of the puddle of water. Okay, and you have this length x, and see how length x changes over time. Then he draw a graph to show how the length of the puddle changed over a period of 4 hours. Okay, so in this case, from the graph, it was observed that the length of x decreased the fastest. Okay, so if I were to show you this, decrease the fastest, right? It means this part. Okay, then what it means is that if I were to draw between 7 and 8, this is 7 and 8, this is a decrease. This is 8 and 9, this is the decrease. 8 and 9, then this is 9 and 10. This is the 9 to 10, this is decrease. So you can see that what it means that decrease the fastest between 7 and 8, okay, is this part. The drop is the largest. Then the rest of them, the drop is not as large as compared to 7 and 8. Give an explanation. Okay, so in this portion, when you drop to let's say from 8 a.m., right? This is from 7 a.m. Okay, the outer border. So let's say I am from 8 a.m. Now after 7 a.m., right? Some of them evaporated, right? So 8 a.m. Okay, let's say this is 8 a.m. Then 9 a.m. will be something like this, right? 9 a.m. Okay, do you notice that this part over here becomes smaller and smaller? Okay, this is 9 a.m. This is 8 a.m. Okay, so then the 7 a.m. will have the largest x. 7 a.m. will have the largest x. Largest x is also means that the exposed surface area is the largest. So when the exposed surface is the largest, the evaporation will also be the largest. Evaporation is the highest. So evaporation is the highest, the decrease will be the greatest. The decrease will be the greatest. Okay, in this case. So you can then subsequently, because the puddle becomes smaller and smaller and smaller, the exposed surface area becomes smaller, the rate of evaporation will also become slower, therefore the decrease becomes smaller as well. So in this case, give a suitable explanation is really linked to the exposed surface area. So from 7 to 8, the exposed surface area is the largest, so the water will gain heat the fastest and evaporate the fastest, causing X to decrease the most as compared to the other time interval. So actually for this part of answer is good enough. The exposed surface area is the largest, so the water gain heat fastest and evaporate the fastest. That's why the drop is also the largest. Okay, draw another curve on the graph above to show how the length of the puddle of water would have changed during the same period on a cold day. Okay, on a cold day, the temperature of the surrounding will decrease, right? So the rate of evaporation will also decrease. So when the rate of evaporation will decrease, right, that means the drop in curve, right, will be much lesser. Okay, much lesser in this case. So this is how it will look like on part B. So let me draw this part out. So it will more or less look something like this. It will be more or less very similar to this curve over here. Very similar to this curve, but in this case the shape must stay the same. Okay? But in this case it will be placed higher, so it will be something like this. So you still need to make sure that the shape is more or less the same, okay, when you are drawing this curve. So this is for part B. Okay, it can be slightly a little bit lower here or here, but it cannot be this answer. It cannot be this. This one you are trying to tell me that it evaporates even faster, so this is wrong. Okay, so it must be the green color one. Okay, any answers along this manner will be good enough. Okay, so what can Andy do to reduce the length of the puddle of water more quickly on a cold day? That means I want to make sure that the XCM decrease faster. Okay, we are trying to find a way to make sure that evaporation become faster. Okay, so you can look at it for me from three areas: W, E, and T. And this is nothing to do with exposed surface area. E will be exposed surface area, nothing to do. Temperature is something that you can't really control it. So you can do with W, which is your wind. Okay, wind. So you can try to put a fan beside the puddle of water to speed up the rate of evaporation. Then the XCM will decrease faster in this case. So okay, so with that we are more or less done with this paper. So so you can download the piece of paper on your own in the description link and try it out on your own. Okay, thank you very much.